I'll mainly focus on a career in geospatial statistics and machine learning. And there's a bit of a context, the reason I have to focus on this. So just like Oscar, I also used to work in the underground mines, but my journey did not start in geology. So before geology, I was doing a diploma in metallurgy, and my first job was as a trainee metallurgist for carbon separation at Afrox. And later on, I got an awakening and I went to UJ to do a geology degree. Later on, I think I missed what I was doing in metallurgy, so I went back to do Chem-Eng with specific focus on hydrometallurgy component of it. And of course, I continued while working in different mines. I started in the gold mines in the Free State and moved down to Gauteng, Carltonville. And later on, I did a bit of consulting, also working for some of the consulting firms. And from 2018 to date, I have been mainly in academia. So in summary, that's all my CV. How I got into all these things, there were a number of people who were involved in my career. The first person, I think, is Dave Reed, whom I met by chance, and he recognized me, and he started providing a lot of mentorship. And I'm sure I got into geology because of some of his encouragement that happened over time. So I also met new friends in between, people like Megan Becker. And while at UCT, I met Hartwig Friemel, who was about to leave to Germany. And that's when we spoke about the PhD. And later on, while I was working for Goldfields and Sibanye-Stillwater, I worked with Leon Tolmay quite closely. I was in the geology section. And Leon was the head of department at the time for resource evaluation. And of course, we used to communicate a lot about this. And later on, I also met Ray, who have taken on the role of mentorship going forward since I got adverts. But I think I need to give a bit of context, because every time when a person speaks of machine learning, some people are saying that you are wasting your time. I mean, we still need more data, which we can acquire by drilling and actually come up with solutions. And sometimes some people just are simply saying this is too expensive. It's not even worth the risk. And the most recent one is that you are now trying to dilute our geoscience education with all these applied sciences and so forth. And I just want to use this slide coming from my friend and colleague, Musa Manzi, who deals a lot with seismics and is a geophysicist. So if you, on the left-hand side, what we are looking at is the map of the Wets Basin. And the black dots that you see here, these are diamond drilling holes and any form of holes that were drilled from the 1890s until 1940. So you can see that there was extensive drilling. And in the 1930s and 1940s, there was a huge revolution that was brought by magnetics and gravity, and people saw this as the pinnacle of science and mineral resources estimation, not exploration, not estimation. And to give you an example, in one of the goldfields where I worked, which is the Carltonville goldfield, it was discovered solely looking at the magnetic properties of shales. So you can see that without a doubt, we moved from drilling, but continued with it. It's not like we have stopped drilling, because we're still drilling. You have seen what Oscar have showed. But then we moved to something to see beyond the surface, which was gravity and magnetics. And what happened after this is that mines started getting deeper in the 1940s and 1950s. So people started mining underground. And we all know that gravity and magnetics can only take you so far. So many mining companies and academics and so forth, they used to have champions. And there was somebody who was quite knowledgeable at the time. There's always someone who is ahead in terms of what's happening. And a paper was published by one of these people, which is A.T. Leroux. So I just want to read an excerpt of it here in summary. So he has mentioned to say that a lot of things have happened, and there has been a lot of technology, the same way we are saying now when there's machine learning. In all the papers that I have I have started with a similar line to say that we are now living at the edge of technology and so forth. And it will seem more feasible, as you can see here, that one needs to find a way to optimize exploration. But what A.T. Leroux have mentioned is that in whatever we do, let's stay away from seismics. Firstly, they are too expensive. same thing that we are saying today. Secondly, they are quite useless because if you have dolerite dikes from the Karoo system, this is just going to reflect them away and we'll never get anything. And if we have dolomites, it's also not going to help us with anything. And then lastly, it's only drilling that can actually find out where the reef position is lying or the ore body is lying. And if we do drilling sufficiently, we are going to find what we want. And I'm sure to save himself, he also put a statement to say that circumstances may change in the future that may require us to use seismics. So it's a bit of a contradiction from the fact that we can't use seismics. And I do sympathize with him because, I mean, seismics were quite expensive in the 1960s. But as I have worked in the mines for quite some time in the gas industry, some of them were supplying some of these mines. I have heard a lot of these stories, especially in archives from goldfields, to say that we have sunk a number of shafts and we found ourselves sinking shafts where there is no reef or far away from the subtrop position. And in addition to that, sometimes we have sunk shafts in the same dolerite dikes that we're running away, such as one of the shafts in Carltonville, which were sunk but were never mined. And this now cost mining companies billions of rand. So actually staying away from many things didn't help because in the 1980s, we saw a fleet of trucks that were coming into the country and they were coming to do a detailed seismic survey 10 times the size of what was predicted initially. And the main reason for this is that with the magnetics and gravity, what we're getting is this type of image, which needed a lot of polishing because we could still miss a lot of things. And we applied a lot of mathematics, a lot of statistics, and a lot of new technology to make sure that the ore body model is quite polished up that everyone can see it. So this happened in the 1980s. I would like this to be the most take-home message to say that technologies that are most expensive today or that we're shying away from today, they are going to be some of the things that may save the day. And I'm not saying all of them will succeed, but some of them. What do I exactly do? Because I'm not a geophysicist, so who am I to speak of seismics? At least I can speak of mineral processing and I can speak of statistics and all these other things because these are things that I have done. And I spend more time trying to find logic in geosciences. And how I do this is that I ensure that my skills that I have learned from geology degree that I have done at UJ with Sarah Turnbull and the others is complemented by other sciences that I have had exposure to, such as mathematics, statistics, and coding. And for those who are more interested in geologic, there's a book that was published in 2003 by Robert Frodeman, and he was speaking of geopoetry, mathematics, and logic in geology. And this is actually a very good type of a way to start things because in all the geological problems, be it in the mine, be it in academia, be it in consulting, whenever we're given a task, it has to start with some questions. We don't just accept what we are being told to do, but we need to understand why, what is it that we have to do? So we have to ask some relevant questions to say, what are we trying to answer? And is there a method that we can use to answer this? And is the answer that we're going to provide going to be adequate in a form of a graphic presentation or in a form of a written report? But what we ended up doing as geologists, we went actually on some sort of a rabbit hole, if you want to call this, because what we have done in the early ages of mining and geosciences, the only instrument that was available was an XRF. And with this, we used to analyze both major elements, trace elements, and minor elements. And we evolved over time to say that we can now have new equipment such as ICPMS, among other things, to analyze more elements. So today, as I'm speaking now, one sample that we analyze in a mine can be analyzed for over 60 elements if we want, because I mean, the technology is there. In addition to that, we can also analyze for isotopes and microbeam analysis and so forth. But this actually is not solving our problem. So we have more data at hand on one sample, but we have far much poor data coverage because the focus is shifted from developing more methods that really don't improve much besides gaining an understanding on one sample, doesn't add much value on coverage. Sometimes we also have more details, such as using seismics, where we cover a large area. But when we use seismics, you'll find that our budget is mainly on seismics and not on geochemistry or not on drilling. And we just improve a minor proportion of what we know. But having more methods and having people who can do this type of work actually provide a way to improve the system. And today I'm not going to be spending time speaking of the first few questions that we can ask and things that we can deploy, but I'll speak of more of data-driven approaches that can analyze the system better while providing a localized resolution that we can use. So to do this, this is my toolkit. The first one is the knowledge of geology. The second one is a number of gadgets that include my laptop, include a lot of scanners to acquire data, a lot of field work, including boots and so forth. And also our little friend here on the right-hand side, Anaconda. And I'll spend the entire time of the presentation focusing on these tools and how we can apply them to solve some of our long outstanding issues. But I think it's important for anything to say that if I was to present any talk in machine learning or a career in machine learning, I also need to show you how things are done, as much as I won't spend time on any type of a code today. So what we have is a number of gadgets to a point where we don't even know which one to use. And if you're working in the industry, you can say, well, I have limitations because I only have a Kleiner rule and a compass Kleiner and all these other things. But when you are in academia, you have more tools because we have all forms of instruments and all forms of physical equipment. And with these gadgets, the type of thinking, including from some of our colleagues and some of our students, is that this artificial intelligence, if it works, we just need to take whatever data set we have, feed it into this AI engine, and we get solutions for our problem. And unfortunately, this is the same type of adoption that some of the industry players adopt. And this leads to one business model, which is called the DNA or do not adopt model, because things will fail. You will give somebody data and you'll expect solution and you'll expect it to give you some profits, but you're forgetting that there's work that needs to be done in between. So to me, I would like to summarize AI by modifying this slide to say that what we tend to do is not replacement of our geological knowledge, but is augmentation of what we know in geosciences. And how we do this is we still have to go to the field. You have seen Oscar showing images of him and his colleagues collecting samples in different parts of the continent and abroad. We still need to acquire data. So we still need people who can deal with data acquisition and analysis. We still need people who can realize value in our legacy data that were collected in old reports. Some of them are not computer readable or machine readable. And we still need somebody to have that bigger vision to say that now that we have collected this data, what do we do with it? And after that, this is where more work starts, building up from the work that was done primarily in the field. And the first one is we need to understand the setting of the data, the structure of the data. We need to do a lot of cleaning, so we still need a lot of data engineers. And in geosciences, we have a lot of people dealing with database management, and we need those people because without them, there's no machine learning and there's no artificial intelligence. We need to standardize the data. The other thing that people tend to ignore is that if I have an algorithm in machine learning, and I have seen this from people that I have assisted or companies I have worked with, where if we have analyzed something, whether we have geophysical data or geochemical data, people just want to inject it into the algorithm and get a solution from that. But there's a lot of future engineering that needs to be done. For example, if I'm dealing with igneous rocks, I still need to have some nickel, and I also need to have some zircon to also know whether I'm dealing with a felsic rock or I'm dealing with mafic rock, so I can get elemental ratios and use them to feed into the machine. And without fundamental geosciences, I don't think you will be able to do any of this part. But then the most difficult part, which in my opinion is missing much from the geoscience curriculum, is the mathematics, statistics, and the coding-based approaches, which is more on the modeling side. I must say that most of the geoscientists learn modeling when they start working in companies that they use commercial software, and some of them don't even know how these things really function. They have attended some workshops that show them how do you press the button and how do you produce a cross-section of some kind, but there is more work to do into this, and machine learning allows you to have that. So it's only after you have done this, you can move to deployment, and also in deployment, there's a lot of testing. So you will see that there's more things, and there's a lot of constraints in applying machine learning in many things. There is issues of data access and privacy, legal ethics, transparency. There's also a lot of bias from some of these algorithms. And then lastly, there's issue of security and trust. Because if you get it wrong once, there's a chance that the company you're working for never forgives you. But as part of a career in machine learning and spatial statistics, you spend 90% of your time doing what we call cognitive learning, which is mainly pattern recognition, if you want to think of it like that. So you start noticing patterns in many things. So when you go to the mine, if it's a gold mine, you start noticing channels, terraces, and all that. If it's a platinum mine, you start looking at places where the contact between the footwall and the hanging wall changes, and any form of internal waste, and where potholes are located and so forth. So the same thing happens when you have to work with machine learning. You will notice that nature is quite predictable and it has similar features. And this is actually something that you should take note of, because if we're looking at the tree branches and so forth, you can see that they are forming some sort of a uniform structure that you can see regardless of the type of the tree. And if you are looking at the other one here, just the branches themselves, they have exactly the similar structure. And if we look at the human nervous system, you'll also see exactly the same thing. And if we move to the right-hand side and we look at natural systems that were formed by geological processes, we can see a global, a national scale of the South African catchment system, and the same scale type of system that you have seen in the human nervous system and the trees. We can also see this in a single river. So this actually tells us that there is actually a spatial structure that nature creates for us, which is a form of a clue on what we need to do in modeling. So many geological features are produced by processes that may be quite complex, so they can vary from millimeters to kilometers. And as you can see here with the catchment system or the tree itself, but these things appear like fractals, because regardless of the scale that you look at, you're still looking at the same thing, same type of patterns. And this can be quite dangerous if you apply machine learning or data science without any context. And by this is that if I was to give you data that is full of this type of structures, chances of you either identifying whatever the outcome is as a human nervous system or a tree or a river are quite high. So this is why it's important to still remember all those geological basic features of what makes a river. So instead of focusing on just simple, detailed functionalities in terms of, instead of analyzing only one sample and expect to get the bigger picture, we still need a larger coverage that can help us to zoom in and zoom out to notice these fractals. So to do this, I think it's far much better for me to give you a couple of case studies with the time that is remaining. And this is mainly to look at integration of geosciences into and machine learning to come up with something. So the first thing to tell you is that whatever we're doing in machine learning is not really new. It may be new in terms of exposure for many people, but if you can check here in the 1950s or the late 40s, Danny Krieg was already doing a form of machine learning, which has become known as the Gaussian processes algorithm in machine learning. And at the same time, there was a lot of work that was being done by people like Arthur Samuels at IBM, among other places, where they developed or adopted a form of machine learning that take cognizance of the existence of decision trees and neural networks. So over time in geosciences, we have been adopting this. The reason this is not popular is that most of the time, this is either adopted by mining engineers, because at least they get exposed to statistics and machine learning and statistics and mathematics and a bit of coding, or this is done primarily by software creators who are computer scientists and have limited exposure in geosciences. So we are the ones who come with the concepts, but we don't see our concepts coming to practice simply because of our limitation in terms of our education. And to give you an example why machine learning is quite important now is that if you are working in biological sciences and you're dealing with genomics or gene sequencing and so forth, there's actually tons of data that you get, but actually the cost of that is quite high. But if you are somebody who is trading stocks, I mean, you just simply need a subscription license and they'll give you all the data and you trade for free for billions of data sets coming from everywhere. And also, if you are in the marketing space, you will notice that if you buy customer database, I mean, the ID numbers don't change. People can change their cell phone numbers and their address. So that data set can be used for a lifetime as long as those people exist. But in geosciences, there's a limitation because it depends on the scale where you are looking at things. So what you will notice is that for each and every data point, because we're now getting more data, it's becoming more expensive to analyze one data point than it is to actually do an overall survey. And we can look at any form of surveys here to say that if we're doing geophysical surveys, this is the amount of money that you can spend actually in US dollars per day. If you are doing geochemical surveys in a larger area for a number of samples, this is what you can spend per sample to get all this data, almost 10,000 US dollars per point. And if you are doing major geological surveys that include many things, including reports and so forth, we're now talking about millions to billions missions. And if we're talking about NASA type of missions, again, it's geosciences, but you're spending more in satellite imagery. So what do we do next? What we need to do is to find a way to use this data. And there's many things that we can do. But doing this, it starts from the education itself. It starts from the willingness of the company to invest in data-driven type of techniques and sensors and anything that has to do with this. It also involves upskilling or retraining of some of the people who are keen or interested into this type of disciplines. So to show you a few examples, many times I work with data that is quite complex, and sometimes I have no clue where the data comes from. And I do ask a lot of questions of where the data come from, how it was acquired, and so forth. And typically when people send you data, it comes with some sort of a QA, QC report of some kind, but not always are these QA, QC reports correct. So we have developed something which is based on topological network analysis. So with this, it's an automated outlier detector that sifts through a data and builds a pattern of network topology, the same network that we see in electricity and in phones and anything else, or in how people interact and so forth. So the same algorithm can be applied in geosciences to map up patterns. And we can also use this for geodomaining, because this also matches things on the basis of variant similarities between population. But on top of that, this can also identify outliers. So data points that even if they have passed QA/QC, they are either nuggets or they're actually not plotting to the general population that we have. So that's one of the applications we can have. The other thing that I can do, or that we can do, is that in machine learning, if you just apply it as if you are working in a marketing type of environment, you'll notice that your models are not really applicable. So you need to exact condition your models to make sure that they are spatially cognizant, so that what you do with this data, once you can understand your errors, you can quantify them and translate them into block models. So what you're looking at on the right-hand side is actually a combined machine learning simulation that takes from some of the sequential Gaussian simulation capabilities in geostatistics with the input of machine learning algorithms to give you uncertainty on how your grade is distributed in your ore body. And you can automate this whole thing to see all the possible occurrences of your grade in your ore body. We recently completed a study in Canada. So this was on prospectivity mapping. And we were given some sort of data, and our ultimate goal was to find out if we can detect any presence of deposits or any potential mineralization. Those who have done mineral prospectivity map or potential mineral maps, they will say that this is based on a classification type of a problem where you need a number of ore deposits that are known. And from this, you need to use them to learn how to predict other deposits. Myself and Stephen Zhang, we have reinvented this and identify the problem in a different manner and find a way to solve it without having to look for data for the existence of existing deposits, because the main aim of prospectivity mapping is to highlight areas that may have some potential of mineralization. So the main problem here in Canada, in the Churchill province and Québec and Labrador, it was mainly to identify hotspots for rare earth elements mineralization. And with this, there is a lot of this very complex geology. So we have all these basement rocks from the Superior Craton. And on top of that, we have a series of igneous rocks that you can see. But on top of this, we also have some of glacial deposits that are covering much of the area. So fortunately, the NR Canada, or the Natural Resources Canada, invests a lot of money in drilling on sampling and geophysical surveys. So we're given that form of data. What we have done, we looked at the traditional approach, or the so-called Gransky approach for compositional data processing and principal component analysis to prepare maps. And we noticed that this technique does work, and I'm not saying it doesn't work, but the problem is it does not enhance possibilities or areas that are typical hotspots. So we had to create our own novel formulation combining known machine learning algorithms, including our own formulation, which we have been doing for a while now. And with this, we take cognizance of the fact that we're dealing with compositional data if we have geochemical data, which many people have to do CLR, or centered log transformation. And of course, we write our own algorithms. And what we simply did was to do the predictions that everyone does in machine learning. And typically, we predicted all the rare earth elements suite, including all the trace elements that came with the data set, and also took cognizance of any form of data that existed. And what we did was, instead of looking at the predictions, we looked at all the deviations of the predictions, because that actually explains where there are potential anomalies. And we took these residuals, we combined them using a novel method. And what it simply did within the area of Labrador and all that, it highlighted typical hotspots, which a typical traditional method for mineral probability mapping wouldn't highlight. And the strength of anomalies was compared with the typical PCA analysis, which is here. And you can see here the PCA-based method. What is showing is that almost everywhere there's anomalies, which is not right. And using our method, we could streamline exactly where, without even manipulating the data manually, using an automated technique where a particular rare earth element deposit is located in this area. And if you look at this scale here, you will notice that these are hundreds of kilometers. So we are not dealing with something that is one particular mine scale and so forth. And this, when they did the validation with the known geology and known mining within the area, our anomalies, which we have picked up using our method, were actually standing out. The other one is that when you do this type of work, people also approach you for a number of things. I told you that I also do consulting work, and I worked a bit for Deloitte, and I also do, part of my job is mineral asset valuation. So another problem that we're given was that a company was buying a new mining asset, and they actually wanted to know, because this asset was quite attractive, to say that what is the probability of maintaining the current profits and what are the chances of making a loss, because the mining company that was selling this asset from them was showing very good projections. So the first thing that you do whenever you have any machine learning problem, as I told you, is to ask some questions. The second one is to choose methods that can work, because you have so many methods. So to approach this, the simplification of this, we use time series analysis, a simple discounted cash flow augmented with something, and then Monte Carlo simulation. And with this, our final results, or the answer, we thought the profit distribution and the probabilities of achieving those profits or maintaining them going forward are high or low. So what we have simply done from this was to look at typical valuation procedures that can be explained in a number of ways. But coming from geosciences, we also need to look at the resources, the reserves, before we even consider the valuation approaches, which I have mentioned here. So in the interest of time, I won't spend more time explaining these methods here, but maybe in the future, if I have to speak on valuation, I will actually do a detailed type of presentation. But all I can say is that we do have some val here in the country, and then we also have many other codes in other places that are governing how valuations are performed. And there's also a valuation triangle that you can see here from the simple methods that look at net present value and internal rate of returns and sophisticated values. But our goal was to make sure that we understand what the client wants. So the first thing what we had to do was time series analysis, which is mainly forecasting of different metal prices and production. And with this, we can build a number of models that is building from known data. So for an example here, we looked at the gold price from 1974, and we looked at it systematically. So we predict from the known point so that we can predict beyond the life of the mine that they have given us, or have some sort of an indication. And on the right-hand side, we're looking at this prediction. So what we have done from this was to take this data combined with others and do a detailed DCF model that actually looks at the cash flow from this for this particular asset, and also looking at the revenue, and do all the projections for the next number of years. Here, I'm only highlighting the first 3 years, as you can see here, because this was done last year. And the other thing that we have done was Monte Carlo simulation, which is quite a very good technique. And I'm happy to explain it as a separate presentation on its own. And for this, we had more than 15 model inputs to check what is the probability of achieving the profits that the current company is achieving. And here on the left-hand side is more of the probability, but I'll use this diagram to simplify it, to say that what you can do to interpret this is to look at the bottom here, we are looking at the profit margin, so the possibility of achieving a particular profit. So if we want to achieve, let's say, just the break even, you'll notice that there's 30% of that. If we want to achieve more than 30% profit, there's about 46% probability of achieving that. So these are some of the things that we can do. What I want to do, because of time, is to rush into the summary to say that to do any of this, I think there are a number of things that we need to do as geoscientists. The first one is there is more things that have been written to assist us. So it boils down to the integration of geoscience education with a number of other things. So the skill sets that I think many people will need to understand or to be able to comprehend much of what's happening in machine learning and to apply them in an industry scale, like some of us are doing, is to look at the concept of deep time, to understand that geological processes are formed over time and things do change because of modification after deposition or after crystallization. And there's papers that have been written by industry leaders, such as Trent in 2000, when he spoke of the layman's knowledge of deep time and why geoscience matters. And there's also some papers that were written about system properties to say that when you are analyzing an ore deposit of some kind, even if you are doing just a resource and reserve model or estimation model, you need to know what sort of processes serve as the prerequisite of what you are going to be estimating. So that was followed up by complex earth processes publications that you can see in here. So I will leave all these for everyone who wants to read them. But later on, there has been more emphasis from 2009 going forward to now on spatial type of analysis, because you can't do any machine learning without understanding spatial statistics. So lastly, or to conclude, you can summarize all these things that I have mentioned to say that the geoscience education does need a bit of statistics and mathematics, not just as first-year auxiliary courses, but as something that equip the future geoscientists to do something. We still need our discipline expertise. Again, you need to learn how to think holistically to be able to notice patterns at a bigger scale and a smaller scale. And lastly, you need coding. Coding doesn't have to form part of the curriculum, but it's something that should be encouraged, that people should learn over boot camps, among other things. And with this, I would like to thank everyone who have joined us today.